Hi everybody and welcome to this video. My name is Carlos Estrada and today I'd like to demonstrate some logic gates in Minecraft using two different methods. The first method is simply using the levers to provide the current to light these lamps, and the second method will be using some kind of constructed transistor using the comparators and the repeaters. But first let's see how to make these simple logic gates using the levers which provide the current. First of all, we have the NOT gate, which is probably the most simple gate. Here we provide an input which can be a 1 or a 0, and depending of this input, this will produce the opposite output. So here we have a 1, it produces a 0, which is the lamp off. And this is done simply with our redstone torch with this brick. When this brick is powered, the redstone torch turns off, which then produces the 0 output. If there is no power here, the redstone simply, it's in its default state, which is on. As you can see, it's on, and it powers a block, so it works as an kind of an inverter of the signal. We'll use this concept later. The second logic gate, which is probably the second most simple after the NOT gate, is the OR gate. In the OR gate we have simply two inputs, which is these two levers, and we simply combine them into one single input. So either of these levers are on, it's going to produce a 1. If both are on, it's still going to produce a 1. Just one is on, still. The only case when this is off is when both of these levers are off. And the third gate we're going to see is the AND gate. And the AND gate, using this kind of logic gate, is a bit interesting. What we have here is two inputs and it produces a single output. So when both of these are on, it's going to produce a 1. How this works is each of these levers powers a redstone torch. So when this lever is on, it turns this off, and then it turns this off as well. And when both of these are off, this redstone right here is going to be off. So this redstone torch here is on powered, so it's on, and it produces 1. And the only case when this redstone is off, which is required for this to be on, is when both of the levers are on. If we turn this lever on, this redstone is going to power this one, and it's going to turn off this torch right here, which produces a 0, the same as this one. So the only case when this one is off is when both of these are off, so you produce a 1. So it's kind of counterintuitive. You need these two to be off, and that only happens when these levers are on. And then we have the NAND gate. The NAND gate is exactly the same as the AND gate. However, we got rid of the torch because we want the opposite behavior. So this one is going to be off when both of these are on, and it's going to be on otherwise, which is the exact opposite behavior of the AND gate. And how this works is we have the very same behavior, however we get rid of this redstone torch. So either one of these, when either one of these torches are on, it's going to be to light this on, and the only case when both of these are off is when we have the two inputs as true. So that's the NAND gate. And for the NOR gate, it's pretty simple. We simply took the OR gate, we combine both inputs. However, we invert the signal using the NOT gate, as we saw at the beginning. So it's simply an OR gate with a NOT gate in the output, which produces the exact opposite behavior of the OR gate. So this is going to be off unless both of these are off, which then produces the on the lamp, which is the exact opposite behavior as the OR gate. And this is how we can create logic gates using these simple mechanisms of using the levers as for providing the current. These logic gates are very useful because they are very compact and they can be put together in many different ways to create more bigger things without using that much space. However, there is another way of making logic gates, which is done using the concept of transistors, which is how they are done in real life. But first, how do we make a transistor in Minecraft? It's more of like simulating the behavior of a transistor. For that, we have here a transistor test. But first, we need to understand a little bit how a transistor works. A transistor has three parts: the collector, the base, and the emitter. So the current comes from the collector, and if the base has a current, it will let the current flow from the collector to the emitter, and we will have a flow of current. If the base is off, it blocks the signal from the collector, so we have no output. So the base works as a switch. If there is a current in the base, we let the current go through the transistor. If there is no current, then we block the signal. It works like a switch, on or off. So we can replicate that same concept in Minecraft using redstone. So here we have, for example, our collector, our current, and here we have our output, the emitter. And this can work as the base. So if the base is off, it blocks the signal and the lamp is off. If the base is on, it lets the current flow through and the lamp is on. To understand how this works, we first need to understand another way to create an inverter. An inverter simply creates the opposite of what you put in. So here we put a 1 and creates a 0. We put a 0 and it creates a 1, which is exactly the same behavior as the first inverter or the NOT gate we saw at the beginning. So we put a 1 and creates a 0. We put a 0 and creates a 1. And to understand this, we need to know how comparators work. This is a comparator. If you didn't know by now, a comparator takes two inputs. This is the base input, and this is the input to which it will comparate the signal, and this of course is the output. So if the signal strength from this side is stronger than the signal strength from the base, this will block the signal and it will produce a 0. So if this signal is stronger than this one, the comparator will block the signal and produce a 0 as an output. So you might be asking yourself, what is the signal strength? Well, the signal strength is measured in how many blocks away is the source of the current from the comparator. The closer, the stronger the signal. So in this case, the torch is 1, 2, 3, 4 blocks away, and the lever is 2 blocks away. So the signal from the lever is stronger, and it blocks the signal. So it blocks this current going through here, and it produces a 0 as an output. If we turn this off, and then the signal here is weaker than this one because there is nothing here, it will simply let the current go through and power the block. So as you might be noticing by now, this is like the opposite behavior of what a transistor should do. We can imagine this is the collector and this is the emitter, and this is the base. So if the base is true, this should be true, but we have false. If this is false, there's no current here, then we have a current here. So we are experiencing like the opposite behavior of what a transistor should do. So how can we fix this? Well, maybe we can add an inverter in here so that it produces the opposite signal of what you put here. So you put a true here and you should get a true here. Maybe we can achieve that with an inverter right here. Well, that's exactly what I've done here. If we can see here, we have a comparator and an other comparator. So if we put this true, the comparator will output nothing as 0, and we will let the current flow through and light the lamp. If we put here no current, there will be a current right here which will block the signal and produce a 0 as an output. So how do we achieve this? We can achieve this using another current, which I like to call the blocking current. This current blocks this comparator and produces a 0 as an output. So what do we want? We want to block the blocking current. So when we turn this on, we are actually blocking this current that goes through here. We are blocking it with this lever. So we have a 0 as an output here, so there is nothing to block this one, so we have the current flowing through. So as you can see, we now have the behavior of an actual transistor. We put a 0 here and the current is blocked and you produce a 0. We got a 1 here and the current can go through and you have a 1. So this is how a transistor works. Now, using this same schematic, you can then construct logic gates out of this. And the first and probably the easiest logic gate you can make using transistors is the AND gate. How does an AND gate work? Well, an AND gate is simply two resistors in series. So if one resistor blocks the current, the whole current is blocked. So both of the transistors need to let the current go through so we can have the output, which is why they are put in series. So if both of these inputs are true, we're going to get a true. If either one of these is false or off, we are going to get a 0. So let's see how this works. Let's follow this input right here, and we have here our blocking current, as I explained it before. This blocking current will block this current right here. This is the main voltage, this is the main current that will light this lamp. And if we have 1 as an input, this input is going to block this blocking current. This repeater is just to maintain the signal strength from traveling this long, so we can have full signal strength right here, and it can actually block the blocking current. So it blocks the blocking current, and there is no current right here to block the main current. So it just simply lets the current go through, which as you can see, this is like a more compact transistor as the one we saw earlier, but it's exactly the same principle. We have a blocking current, we have our input which blocks this blocking current, so there's nothing to block this comparator, and we let the current go through. And the same is true for the other input. If we follow it right here, we have here our blocking current and our comparator, and as there's nothing to block this signal, it just lets the current go through. And if both of these comparators are letting the current go through, well, we're going to have a 1 as an output. And that's how it works. We have one transistor here and one transistor here, both connected in series. Sorry. So if we turn this off, for example, we're going to let the current go through here. By the way, this is just powered by a torch right there. We let the current go through here, but as the blocking current is passing through here and it blocks this comparator, the current gets stopped right here and it produces 0 as an output. And the same is true with if we turn off the other one. The current is simply blocked in here and it produces 0 as an output. It doesn't matter if this one can let the current go through, because there's no current to let go through. And that is how you can create an AND gate using transistors. And the second example of logic gates is the OR gate. Well, the OR gate is simply two transistors connected in parallel. So the current now has two paths to choose. If either one of them is blocked, it can go through the other one. So only one of the paths needs to be open for the current to flow. For example, here we have one input on and the second off, and we have a 1. If we have both on, we still have a 1. But if we block both, we have a 0. As it works. And how it works, we have two transistors here. Here's one transistor, here's the other transistor. And here we have our main current. So the main current goes through here, and if the input is true, it's going to block the blocking current. So there's nothing to block this comparator, and it just lets the current go through and power this block. And the same is true for the other side. We block our blocking current, so there's nothing to block this comparator, and it just lets the current go through and power this one. If we were to turn this off, then the blocking current goes through and it blocks this comparator, so the current right here is not able to go through. This signal you see here is actually from this side. It's not actually from this one. So if we put both on, we have the signal from two sides, but if we turn these both off, then the signal has no path to go through, so it's simply a 0 as an output. And another logic gate we can make with this is the NAND gate. The NAND gate, as you can see, is simply an AND gate, as we saw before. Here's one transistor, here's another transistor, and both connected in series. However, we add an inverter to the signal, to this AND output. So with this inverter, as we saw earlier, we simply negate anything that comes from the AND gate and produce exactly the opposite output. And the NAND gate is going to be true in every case except when both of these inputs are true. And well, this inverter is as we saw earlier. Here we have our input, and if this signal is stronger than this one, it's just going to block this signal and produce the opposite output right here. And we can also create a NOR gate, which is exactly the same as the OR gate. We can see one transistor right here, the other transistor right here, connected in parallel. However, we use an inverter to invert the signal and produce exactly the opposite output. So if we have one true and one false, of course we're going to get one false, and it's true only when both of these are off. And well, following up, we can also create a XOR gate. A XOR gate is only true when only one of the two inputs is true. So if this one's true, it's going to produce the true output. But if both of them are true, it's going to produce the false output. And the way the XOR gate is just following, it's just a combination of the AND or a NOT gate we saw earlier. So as we can see, here we have an AND gate. As you can see, the two transistors connected in series. Here we have another AND gate, and these are connected to an OR right here, as you can see, in parallel. And here we can also see a NOT gate, which is just the inverter, and the other NOT gate, which is also an inverter. And here we have our output. So as you can see, you can create pretty much everything with these gates using transistors. However, disadvantage of this is that it takes up a lot of space. As you can see, using transistors for logic gates takes much more space than the other logic gates which we saw at the beginning. And by the way, there is also another way to create the XOR gate using the comparators in this arrangement. However, these comparators are put in the subtraction mode. The subtraction mode is when this redstone is lit up. And what the subtraction mode does, it simply takes one input right here, the other input right here, and it outputs the subtraction of these two strengths. So if the strengths are the same, it's going to produce a 0 as an output. So, however, for example, when both of these inputs are true, these two XOR gates are going to receive the same signal strength from both sides, and they are going to produce a 0 as an output because the subtraction of themselves is 0. However, if we turn one off, then what happens? The signal goes through here and only through here. This comparator is going to receive the same signal from both sides, and it's going to produce a 0 as an output. However, this comparator right here is going to receive a stronger signal from this side than from this side, because this one is closer to the source than this one. So it's going to produce something else that is not a 0, a positive value. And this positive value powers this repeater, which then produces the output. So when are the cases when this produces a 1? Only when one of these is on. If we turn these both on, then both comparators are going to receive the same signal strength from both sides, and both of them are going to produce a 0 as a subtraction. So we're going to get a 0. So we need only one of them to be on for this to work. And of course, if we turn both off, well, there is no signal at all to compare, so we also get an off. And as I was playing around, I decided to make a 2-bit adder. This 2-bit adder uses the logic gates we saw at the beginning, these logic gates, because they are much more compact and much more easier and faster to build than the transistor ones. So I just created a 2-bit adder, and let me show you how it works. This 2-bit adder takes two numbers as an input and produces a number which is the addition of these two numbers as the output. So in this side we have one number, which is the first digit of that number and the second digit of that number, of course in binary. So for example, if we have this, we have a 1, because this is 1 and 0. If we have this, we have a 2, because this the second digit is 2 and the first digit is 0. And if we have this, well, we have 1 plus 2, which is 3. So we have a 3. And this is the second number that we want to add, the first digit and the second digit in binary. So for example, if we want to add 1 plus 1, the output right here, of course in binary, it's going to be, this is the 1 and this is the 2, so you have to add 2. And of course if we add 1 plus 0, we're going to get a 1. And what if we add, for example, 2 times 2? Well, then we get a 4, which this in binary represents the number 4. And if we add 2 times 3, we're going to get a 5. This is the 5 in binary. We add 3 plus 3, well, we're going to get a 6, because this is the 2's and this is the 4, and 2 plus 4 is 6. And well, the way this works is simply using the schematic of the half adder and the full adder. As this works with only with 2-bit numbers, you only need first a half adder, and then you provide the full adder with the second digit. So for example, here we have the, this is B0. So here we have the first digit, and the first digit is used as an input in an XOR gate. This is XOR gate using the 2 comparators as we just saw, and it's used in the XOR gate with the A0, which is also the first digit of the other number. So they're used in the XOR gate, and this output gets to be in the first digit. And for the carry of the half adder, we simply take that same signal from both sides, we take it up here, and we put it in an AND gate. We can see this is an AND gate, the first AND gate we saw with its redstone torch, and that produces the carry. Then we use the carry to add it to the result of B1 plus A1, right? So let's follow B1 and A1. This is B1. So here we have B1, and it's used as an input in an XOR gate together with A1. And then this is used as an input in an other XOR gate, and the other input is of course the carry of our previous sum of the previous digit, which this is the AND gate that produced the carry. So this XOR gate produces then the result, which is used as the second digit. However, there is also a carry produced in this sum, so that's why the input of the previous XOR gate is used in an AND, and this AND is then joined in an OR gate. This, as simple as it is, it's an OR gate, because here we have one input, here we have an other input, and here is the output. So either one of these needs to be true for this to be true. So we make an OR gate of the AND, the result of the AND, and the other AND, which is the AND of the two of a B1 and A1 by themselves. So that should produce the third digit, which is the carry of the second digit sum, which is right here. And of course there is no way to make a fourth digit out of this sum, but I just thought it will look nice and symmetrical to have the other lamp right there. There's really not no use for that one. And last but not least, I would like to show this 4-bit adder. Now the previous one was a 2-bit adder, however this is a 4-bit adder which uses 4 bits for each number as an input and 4 bits on the other number as an input, and produces a 5-bit number as an output. And here are the instructions on how to use this 4-bit adder, but it's pretty straightforward. You've introduced your binary number right here and the other binary number right here, following B0, B1, B2 and B3 as the order of the digits. So this is like the ones digit, it's not really ones digit, and the tens digit, this is not really tens digit, but this is like the units, the tens, the hundreds, and so on. So for example, as we made in the 2-bit adder, let's add 1 plus 1 equals 2. And if we add 3 plus 1, that equals 4. And if we add, I don't know, 2 times 3, that equals 5. And as this is a 4-bit adder, we can create even more and more bigger numbers to add. For example, we can add, this is a 4, 5, and 5 plus 5, for example, creates a 10. This is a 10, this is the 8, this is the 2, and 8 plus 2 is 10. And well, for example, we can make this 7 plus 7 produces 14. This is the 2, and this is the 4, 2 plus 4, 6, and the 8, 6 and 8, that's 14. And you can pretty much add any number up to 31, which is the limit of the 5-bit number. So now let's see how this 4-bit adder works in the inside. And for that, let's add a small number right here, maybe 1 plus 3 to make it more interesting. And first, it's going to add the first digit and the first digit of the second number. So let's follow this signal, these digits, see what happens. So first, we have the B0 and the A0 coming from this side, combined in a XOR gate, and the result of this XOR gate is going to be the first bit result. So we take this signal right here, and it goes directly to the first bit of the result, which is this lamp right here. However, we need to see if this sum created a carry, and for that, that's going to take B0 right here and take the signal before it's being added in the XOR gate and combine it in an AND gate with A0 as well. We take the A signal from A0 right there, and if both of them are true, it means we have a carry, which is the first sum carry right here. And now let's follow the second digits, which is B1 and A1. So if we follow a B1 right here, we see it's being added in a XOR gate with A1 right here. And the result of this needs to be now added in another XOR gate with the carry we got previously. So this is the result of A1 plus B1, and we add it with this one, which is the first sum carry we got earlier. So the result of this XOR gate is going to be the second bit result. So if we follow this signal, we see it's the second bit of the result right there. However, we need to see if either one of those two XOR gates created a carry, and for that let's first visit the first XOR gate, which is a B1 plus A1 coming from there, and we take the signal before it's being added right here and combine it in an AND gate, and this is the result of the AND gate. We need to do the same with the other XOR gate, which is the result of the first XOR gate. We take the signal before it's being added right there, and we combine it in an AND gate with the second signal, which is just the first sum carry. So here it goes to the AND gate, and here it goes to be added in the XOR gate. So we combine this in the AND gate and produce that carry. Now we need to combine both carries of both XOR gate operations to see if either one of those produces a carry. So for that we just need an OR gate. So if we follow this signal right here, we can see it's not so simple to see, but this is an OR gate. This is one input, this is another input, and this right here is the output. So if this one's true, it's going to light this one. If this one's true, it's going to light this one. So it works as an OR gate. And this OR gate is going to be the second sum carry. And this second sum carry is then going to be added with the result of the third digits. However, we know that those third digits, they are 0 and 0, and then we add a 1 to the second sum carry, the AND gate right there, and we produce the output, which is the third digit being laid up, which produces, of course, A4. 1 plus 3 is 4. And that's all for now. I hope you enjoyed it, and until next time.